So today we will discuss on continuity and uniform continuity. So we say a function f is continuous at x naught if the following holds. So given any epsilon positive, if we can produce a delta positive such that whenever x enters in a delta neighborhood of x naught, as this thing happens, this condition should hold. So now this delta is very much dependent on epsilon, and it is dependent on x naught. So delta is a function of x naught and epsilon. Okay, so this is the definition of continuity. And coming to uniform continuity, we say a function f is uniformly continuous if f of x minus f of y is less than epsilon whenever x minus y is less than delta. So uniform continuity is uh, typically defined on a set. For a given epsilon, there is only one delta that exists independent on the location of the point. Earlier definition, we saw that delta is dependent on both epsilon and x naught. The point of continuity in uniform continuity, that's not the case. As long as you find 2 points, x minus y, within a delta, we always have the function difference of the functions limited to an epsilon. So now let's solve some questions on this. So which of this thing is true? The image of a closed set under a continuous function is closed. So this is not true, because we can find a counterexample where we can pick a closed set and the image is open. So in general, um, for continuous functions, the following is true, right? Whenever f inverse of u, let's say f maps from x to y. So f inverse v is for v is open in y. We always have we always have f inverse v open in x, right? So from the first principles one can show that f inverse v for an open v is open in x. For v which is open in y, f inverse v is open in x. This follows from the definition of continuity. But the question that was asked is, do we have if maps x to y and some subset k of x which is closed? Do we have f of k also? This implies f of k closed. This is not true. This is false. And the example that is given is if f is tan inverse x, and take x to be R and x is closed, and tan inverse x we have is minus pi by 2 to pi by 2. It's contained in minus pi by 2 to pi by 2, and clearly minus pi by 2 to pi by 2 is open set. So this is a counter example. Coming to second question. Max of two continuous functions and min of two continuous functions, are they continuous? Right, so we have two functions f and g continuous. Question is max of f comma g is continuous? So this is continuous because max of f plus g, f comma g can be written as f plus g plus mod of f minus g by 2. It's easy to verify. If say at a point f is greater than g, then this will be 2f by 2 and this is f. So the point is this is continuous because addition of two continuous function is continuous, and again the is for this again f minus g is continuous from the similar argument. Then the function mod x is a continuous function. So continuous functions composed on top of continuous functions again continuous. So mod of f minus g is continuous. Again, it again follows from the first thing that addition of two continuous function is continuous. So max of f comma g is continuous. Now same thing for min of f comma g. Min of f comma g can be written as f plus g minus mod of f minus g by 2. Since we take the same thing f greater than g, what happens here is this end up getting f plus g, and this is positive f minus g. We end up getting 2g over 2. So this is g. With the similar arguments, we can conclude that min of f comma g is also continuous. State the following is true or false if a function f is such that like f maps real to real, and the mod f of x minus f of y is less than mod x minus y per beta, and is f is uniformly continuous. Can easily see this. Question is f uniformly continuous? So mod f of x minus mod f of y, sorry, minus f of y less than mod x minus y bar beta, beta positive. Excuse me. So by definition of uniform continuity, we should be able to find for a given epsilon we need to find a delta such that whenever x minus y is less than delta, f of x and f of y is less than epsilon. Right, so, and delta can be only a function of epsilon, not the points under consideration. So can easily see that this is uniformly continuous, because if we make this mod x minus y bar beta is less than epsilon, so this implies mod x minus y is less than epsilon per 1 by beta, and we call delta to be epsilon power 1 over beta, and plug this thing in this definition. We see that this thing satisfies the this quantity. F of x minus f of y is less than epsilon. This comes from this thing as long as we choose x minus y less than delta, which is epsilon per 1 over beta. So this is uniformly continuous. A subset A of R is said to be convex if for any xy um, the 1 minus tx plus ty belongs to A. So which of the following is true? A subset, every convex set is an interval but not converse. Every interval is a convex set but not converse. A subset is convex if and only if it is an interval. There exists a convex set which is not interval, and there exists an interval which is not convex. So we'll do a quick review of convex sets. So convex sets. Say this set domain A. Take a point X and a point Y. Any combination of alpha x plus 1 minus alpha times y belongs to A for all x comma y belongs to A. If this holds, the set A is called convex. Convex set. So in this case, pick any point, and so what happens is if alpha is 1, this combination is nothing but x, and but alpha is 0, this will go y. So basically it interpolates all the points between x and y, with alpha 1 being here and alpha being 0 here, right? So but if we consider this point y, there might be a point that falls out of the set, right, for some combination of alpha. So this is not a convex set, not a convex set. So in R, all the intervals are convex and all convex sets are intervals. Let's check if the intervals with a closed interval a to b and see if this is convex. If this is a convex set. Pick any 2 points x comma y such that a is less than or equal to x is less than y is less than or equal to b. And now it's easy to see that alpha times x plus 1 minus alpha times y belongs to a comma b. So we can indeed pick any point C such that alpha x plus 1 minus alpha y is equal to C, and C is such that x is less than C is less than y, and one can find the value of alpha corresponding to C. So this shows that intervals are convex sets. We now show that convex sets are intervals in R. Take A be a convex set and pick A comma B with A less than B, and we can find a C such that A is less than C is less than B, and we can associate a value of alpha such that is equal to C. So this shows that um, the interval that is formed between A and B is a convex set. State whether the following is true or false. Now, F is a continuous mapping from R to R, and there's a subset U, an open subset of R, is F of U open. So this is explain this. F is a continuous mapping from R to R, and the question is if U is a open subset of R, if U is open, is F of U open. So this is false. In general, this need not be true. So any F inverse of U is open. U is open. And F inverse of U is closed if U is closed. So we can consider an example of a constant function. So F is constant. We can take F of x is equal to C for all x. Now pick any open subset of R, call it as U. Say U. What we have is F of U is equal to C for all x belongs to U. But C is a singleton and it is a closed set. So the question is if K is a non-empty compact set and F is a continuous mapping such that the following holds, F of x minus F of I is greater than x minus y mod. Which of the following statements are true? F is 1 on 1 and F inverse f of k to k. F inverse says that f of k to k is continuous. F in 1 on 1, 1 to 1, but F inverse f of k to k need not be continuous. F need not be 1 on 1, F is surjective. So can be seen that f of x is a given, this is a given condition, and for all x comma y belong to k, and if x comma y belong to k and x not equal to y, then mod x minus y is positive, right? So this implies that mod of f of x minus f of y is greater than 0, and this implies f of x is not equal to f of y. So for any x not equal to y, we have f of x not equal to f of y. This implies that f is 1 to 1. And further, we have this thing like f inverse x minus f inverse y. So these are points in the domain for x and y belong to the codomain part, right? So this is f of f inverse x minus f of f inverse y, and which is nothing but x minus y. So this is following from this statement, x minus y is less than or equal to this. Here this is x minus y is in the domain. That's why f inverse x, f inverse y is takes the role of x and y in this thing. And we have this for all x comma y belongs to f of k, and we put any x naught in the range of f of k and a sequence xn that is approaching x naught. So we have that xn as xn converges to x naught. So we have f inverse x and f inverse y converging to 0. Hence, so f inverse of xn goes to f inverse of x0, and thus the function f inverse is continuous. So there is a general result on this thing. Suppose if f is a one-to-one mapping of compact metric space, x to y, then the inverse mapping f inverse is a continuous mapping from y on to x. State the following if is Q disconnected in R. Can show quickly that connected sets. So two sets are connected if it cannot be written a set is connected if it cannot be written as union of two separated sets. So E cannot be written as A union B. A and B are separated. So what is separated? As A intersection B bar. B bar is a closure of B, and B bar A bar intersection B is an empty set. So the question at hand is Q in R connected? It's not, because R can be expressed as minus infinity to square root of 2 and square root of 2 union infinity. Hence Q is disconnected in R. So f defined by the function f of x is x square. Which of the following is true? F is uniformly continuous and R, this is wrong, and f is uniformly continuous on 0 1 but not uniformly continuous on R, this is true. F is not uniformly continuous on 0 to 1, and f is uniformly continuous on 0 to 1 but not uniformly continuous on 0 1. So here f is uniformly continuous on close 0 1 but it is not uniformly continuous on R. Thing is f maps R to R if and f of x is x square. Um, so for uniform continuity, we need f of x minus f of y less than epsilon for all x minus y less than delta. Can we see that this x square is dependent on the point at which the continuity is being considered? So it's not possible to get a one delta across all the points in the domain to satisfy this. But it is a continuous function when we restrict the continuous function to compact sets. So 0, 1 is a compact set by Henry-Borel theorem, the closed intervals in R. And so continuous functions on compact sets are uniformly continuous. Only continuous. So it's the result follows by this argument.